Okay, before we actually put together a hypothesis test and actually go walk through the analysis, let's talk about the different types of errors that can occur during hypothesis testing. Remember I said we're going to make decisions based on probability. So whenever you make a decision based on a probability, there's always a probability you made the wrong decision. Now when you complete a hypothesis test, you will always either reject or fail to reject the null hypothesis. This is all about rejecting or failing to reject the null hypothesis. Now, in reality, the bottom line is that the null hypothesis is either true or it's false. Let's go back to that cancer research for just a moment. The null hypothesis was that the mean, it was 2.25 years. That's kind of the status quo. That's what's been happening. The alternative hypothesis, remember our sample statistic was 3.1 years. So the mean is greater than 2.25 years. Okay, 3.31 never shows up in here. That's the sample statistic. The question is that 3.31 big enough, far enough away from 2.25 to suggest that we're wrong about the 2.25 and the survival time with this new treatment is actually longer, hence the treatment's better. Now, if we're able to reject the null hypothesis, all that's left is the alternative. So we'll say that's more likely. But if we fail to reject it, then what we're dealing with is a situation where we don't really know which one is more likely. So absent proof that the alternative is more likely, then we just continue on as if the null was probably true. We don't really know for sure, but that's the way we actually treat it. Remember, if we're able to reject it, it being the null hypothesis, this is always about whether you're going to reject or fail to reject the null hypothesis. If you reject the null hypothesis, then you're saying the alternative is more likely, and that's the decision you make. You will go with whatever the alternative hypothesis actually says. Now, remember I said that there's always a possibility of making an error, making a mistake, whenever you make a decision based on probabilities. Now, in reality, the null hypothesis is either true or it's false. If you reject the null hypothesis when it's actually true, that's bad. Okay, that's an error. And this particular error we refer to as being a type 1 error. And the probability of a type 1 error we set as alpha. And we determine alpha, we establish alpha to begin with. And when we establish alpha, you're saying, this is the maximum probability of type 1 error that I think is a reasonable risk to take. Reasonable risk meaning if I reject the null hypothesis, what's the maximum probability that I'm going to commit a type 1 error? What's the maximum probability I'm going to make that mistake? Now this alpha is the same alpha you've come to love and adore when you do confidence intervals. It's the exact same guy. Well, if the probability that you make a type 1 error is alpha, then the probability that you reject when it's actually false, which is a good thing, is 1 minus alpha. So if you say 5% is the maximum error that I'm willing to accept of committing a type 1 error, then that gives you 95% chance, the minimum 95% chance that what you did was the right thing if you reject. Now, the other type of error will occur if you fail to reject the null hypothesis, which is actually false. If the null hypothesis is false, you want to reject it. So if you fail to reject it, when it's actually false, that is what we refer to as a type 2 error. And this probability we designate with the Greek letter beta. That means if you fail to reject a true null hypothesis, which is a good thing, if the null hypothesis is actually true, you don't want to reject it. That probability is 1 minus beta. Now this 1 minus beta is commonly referred to as the power of the test. It's commonly thought of as a probability of doing the right thing. Now beta, we won't actually work with beta in this particular course. Beta is actually controlled by the sample size. The higher the sample you get, the bigger the sample you get, the smaller beta becomes, which means the bigger 1 minus beta becomes. This is actually commonly done in the social sciences with what's known as power calculations. We won't actually deal with beta in this course, but I did want you to be familiar with the idea of beta and the fact that 1 minus beta is commonly referred to as the power of the test. Because that's something you could see in literature, or very commonly we'll see in literature, particularly if you're working in the social sciences. Now, remember I said that we will make these decisions based on probabilities? The probability that we're going to use is known as a p-value. A p-value is the probability of observing a test statistic at least as extreme as was observed. So what the heck does that mean? Well, let's just draw a quick diagram here. And I'm going to use that cancer example. We believe the mean to be 2.25 years. Out here somewhere is our sample statistic, the 3.31. If we find the probability that x bar, the sample average, is bigger than 3.31, believing that 2.25 is the actual true mean, what we're finding is this probability right here in this tail. That's what it means to be at least that extreme. This probability is what we think of as being the p-value. Now, if the p-value is really small, that means that 3.31 is actually quite a distance away from 2.25. The farther it gets away from 2.25, the smaller that tail probability is going to be. When it's close, then the bigger that tail value is going to be, or probability is going to be. Now, what does it mean to be close and far? Well, we've talked about this actually quite a bit in other chapters. The idea of being far away is actually related to the number of standard deviations. If you're several standard deviations away, then you're far away, and the probability of that occurring gets smaller and smaller and smaller. So, let's just pretend for a moment that 3.31 was actually over here someplace. In terms of standard deviations, it's much closer to what we believe the true mean to be, that 2.25, and this would be a much larger p-value. See, as it gets closer, that probability of making a type 1 error gets bigger and bigger and bigger. See, if 3.31 was very close to 2.25 in terms of standard deviations, then it's probably you just saw that 3.31 or you observed it as a matter of chance. So if you reject the null hypothesis, this blue probability is saying the probability that you did the wrong thing is pretty big. Because if you reject the null hypothesis, you're saying you don't think it's by chance. Well, as 3.31 gets farther and farther away from 2.25 in terms of standard deviations, then this probability, this red probability, the probability that it's just by chance gets smaller and smaller and smaller. So the probability of making a type 1 error gets smaller and smaller and smaller. That's why we think of the p-value as actually being the calculated probability of a type 1 error. That's the way we think of p-values. That's the way we actually use the p-value. Technically, they're not the same, but in practice, they really are. Okay, that should give you a pretty good idea of the types of errors that you can make when doing a hypothesis test, and a little bit more insight into what hypothesis testing is all about.